Welcome students. In today's lecture, we will be looking into the manipulator dynamics. So in the previous sessions, we were discussing regarding various type of analysis. We started with the kinematic equation analysis where without considering any of the force or torque that is being exerted on our robotic arm, we were calculating the equations or we were deriving the mathematical equations or expressions in order to describe the motion, and at last we were able to generate the expression or the mathematical expression for the position and orientation of a robotic arm or manipulator's end effector. Okay. Followed by this, using this information regarding the position and orientation of the end effector, we started the velocity kinematics, where using these informations derived from the by applying the kinematic equation analysis, we described the velocity of the end effector or the differential motion information of the end effector, and we related these velocity or differential motions or accelerations imparted on the end effector with respect to the velocity or differential motions that was experienced or imparted on the various individual joints of the manipulator, so that we obtain the final desired position, the velocity, etc. And for this we were making use of the Jacobian matrix. Now, as we know that for every body which has mass, in order to move in a particular linear direction, we need to exert some amount of force. Similarly, if the object or the rigid body can rotate, then we need to exert some amount of torque so that the rigid body gets rotated about an angular acceleration. So in order to relate these two factors of force or torque that is acting on a rigid body, we make use of the dynamic analysis. And since here we are trying to, or we go for establishing the relationship between the force and torque that is being exerted on the robotic arm, so that the motion of the robotic arm is obtained in the desired pattern, we call this as the manipulator dynamics, or the procedure of describing the relationship between force and torque and the motion of a robotic arm or manipulator is known as dynamic equations or manipulator dynamics. Okay. So here we will be making use of the informations with respect to the position orientation which we have obtained from the kinematic equation, as well as the velocity information which we have obtained from the velocity kinematics. So the dynamic analysis performed here is basically applied in order to derive the equations of force or torque that is needed in order to induce the desired accelerations in the robotic joints and links. Because we know here currently we know the position orientation, the desired position and orientation by applying the kinematic analysis. Then by applying the velocity analysis or velocity kinematics, we were able to determine the amount of desired accelerations, velocity, or the differential motions at each of the joints that is present on a robotic manipulator. So here we are going to apply this analysis in order to derive the equation which gives you the expression for force and torque that is needed in order to induce the desired amount of acceleration or velocity at the robotic joints and links. So these equations can be further used in order to examine the effect of differential inertial loads on the robot, and depending on the desired acceleration we could end up at a conclusion whether certain loads which is present on our robotic arm or manipulator is important or not. So this analysis is further taken in order to study about the effect of various loads that is present on a robotic system, which is going to affect the performance of a robotic manipulator. So while the robots are being designed for space applications, this factor is of very important, because it we need to know which are the loads which is going to affect the performance of the entire system. So this dynamic application or manipulator dynamic analysis seems to have a large amount of implication or application on the design and implementation of a robotic system. So by knowing the importance of each and every components, and the uh, importance of components means the loads, a robotic designer comes to conclusion on the relation between various elements present on the robot, and he can appropriately design those components such that the required performance is obtained from the system. So before going to the analysis, we need to have some basic concepts or basic knowledge about the equations which governs the entire analysis procedure. Okay. So we have studied these equations in our early early classes of mechanical engineering or the basic course of dynamics. First one, the accelerate. If we need to accelerate a mass in a particular direction, we need to exert some amount of force, and this is defined as sigma f is equal to ma as per the Newton's law, where force is equal to mass into acceleration. So if there are a number of forces that is acting on that particular mass, then we can collectively say that the summation of the entire forces that is acting on the mass is equivalent to mass into the acceleration that is induced in that particular mass. Similarly, for a rotating body, if you take a rotating body, respective of the mass, it's the angular acceleration which leads to the rotation of the rigid body. So in this case, an amount of there may be different torque components which affects the angular acceleration to be induced. So we can say the summation of the entire torque that is acting on the rotating body is equal to the product of moment of inertia multiplied by the angular velocity or angular acceleration. Then the basic concept of kinetic energy. So when we take a system, the total kinetic energy that acts on a system is defined as summation of linear kinetic energy as well as rotational kinetic energy. It's the case where the system consists of both some linear components as well as some rotational components. So this is the case of a robotic system. So in our system, all of our robotic systems contains most of the robotic system contains some amount of linear as well as some amount of rotational, and there may be exceptions where there will be only linear actuations and where there is only rotational actuation. So based on that, we have to take a final decision. So here the basic concept is that the kinetic energy of the end of a system is defined as the total of the linear kinetic energy as well as the rotational kinetic energy, where the linear kinetic energy is equivalent to the kinetic energy that is experienced by a simple pendulum, that is half mv square, and the rotational energy experienced by a system is defined as half of the product of inertial energy multiplied by the angular velocity square. Okay, so first one, mv square, where v is a linear velocity. Both of these linear velocity and angular velocity has been expressed, or the expressions of these velocities has been expressed by in terms of robotic system in our velocity kinematic topic. Okay. Then coming to the potential energy, the next system that energy that is playing on our system is the potential energy, which is defined as mass into gravitational force into the height of the system, so to mgh, which is a basic concept. Then if we consider the potential energy of spring, okay, it is for a system with a rigid body of a rigid body. Now coming to a spring, the potential energy of a spring is defined as half k into x square, where k is a spring constant and x is a linear displacement that is observed on the spring. Okay. Now, to this point of view, as per your syllabus, we need to calculate the moment of inertia in case of the kinetic rotational energy. So for that, there are two cases in most of the robotic systems. One is the moment of inertia at the center of the road, because we consider the links of a robotic system as roads, okay, or a thin road. So if the moment of inertia is been applied or it is been exerted on the center of the road, then it is defined as I center is equal to 1 by 12 ml square. Okay. And if the moment of inertia is applied with respect to one fixed end of the road, then we can say I end is equal to 1 by 3 ml square, where m is the mass of the road and l is the length of the road. So the derivations with respect to the basic equations can be obtained from the uh, books related to the basic concepts of dynamics or basic mechanical engineering. So coming to our topic, so in case of robotic systems, there are two different methods by which we can apply this dynamic analysis on a robotic manipulator. One is the Newtonian mechanics and the other one is the Euler-Lagrangian mechanics, or which is commonly known in the term Lagrangian mechanics, or LM. Okay. So in case of Newtonian mechanics, the analysis procedure is based on the Newton's law. So as we know that Newton's law are based on mass and acceleration of the system. So if we are going to define the dynamic equations of a robotic manipulator using Newtonian mechanics, we need to concentrate on the mass and acceleration that is acting on the system. And but this method is not suitable, or it seems to be a difficult task in case of non-distributed mass systems. So it's it is more similar for non it is best suited for non-distributed mass system. And if we have a robotic manipulator in which the mass is being uniformly distributed, the analysis seems to be difficult for a complex robotic manipulator. Okay. So we normally apply this Newtonian mechanics for robotic manipulators which has non-distributed mass systems. Whereas when we go for Lagrangian mechanics, the analysis or the procedure of deriving the dynamic equations of a robotic manipulator by applying Lagrangian mechanics is based on energy that is acting on system. So here we need to focus on the kinetic as well as the potential energy that is exerted on a system. Okay. And if you look to the uh, application complexity or the analysis complexity, we can see that it's suited for both distributed and non-distributed mass systems. So it is been widely used in case of robotic manipulators, because in some cases we may be having the robotic system with distributed mass system, and in some cases it may be having with non-distributed mass system. So in general, for both these systems we can have the Lagrangian mechanics. But this mechanics, and if you look to the complexity, it seems to be much complex in simple systems when we are applying the Newtonian mechanics while comparing with the Newton mechanics. Okay, so in case of simple systems, Newtonian mechanics is better, but as the complexity increases, Lagrangian mechanisms seem to be more simple than the Newtonian mechanics, as well as we can see that Lagrangian mechanics can be applied irrespective of the mass distribution on the system. So in our lecture and as per your syllabus, Lagrangian mechanics is the method or is a basic concept which has to be followed for deriving the dynamic equations of the given robotic manipulator. So coming to the basic concepts of Lagrangian mechanics, as we told, it's based on the energy of the acting on the system. So the Lagrangian mechanics or the mechanic equations or the set of dynamic equations that is derived using Lagrangian mechanic concepts is based on the differentiation of the energy terms with respect to the system variables and time. So if we take the robotic system, we would have two system variables. One is a variable corresponding to linear motion, and the other one is a variable corresponding to the angular motion. So by differentiating the kinematic, kinetic and potential energy terms with respect to the corresponding variable, okay, that is acting on a robotic manipulator, if it has both linear as well as rotational movement, we need to differentiate with respect to both the linear variable or the prismatic variable di or xi, and if it has some revolute joints, we need to differentiate the energy terms with respect to the angular variable or the revolute variable, that is theta normally we use, as well as we need to differentiate these terms with respect to time also. So as we already told, this method seems to be a difficult process for simple systems when compared to Newtonian mechanics, while as the system complexity increases, it seems to be relatively simple. So these are the two generalized equations that is used for deriving the dynamic equations of the given system. So if our system has only linear motion, we will be having only the equation of force. Okay, for a linear motion, there will be only force, there won't be no rotational motion. So this expression for torque that is acting on the system is equal to 0. Okay, so if there are n number of linear joints, then the total force that is exerted on the system to move, okay, to move that entire system is defined as the summation of the entire forces, and each force element is defined by Fi is equal to dou by dou t of dou L by dou x dot minus dou L by dou xi, okay, where xi is the system variable corresponding to the linear motion I, and Fi is the force that is induced on system due to the linear joint xi, okay, and where L is the Lagrangian constant, or not a constant, it's a Lagrangian parameter L, okay, which is defined as the difference between the kinetic energy and the potential energy that is acting on system. Okay, similarly, if you go for the rotational motion, if your system is having, for example, if I am considering a 1 degree freedom which has only linear joint, then there is only one equation, F1 is equal to dou by dou t of dou L by dou x1 dot minus dou L by dou x1. If there are 2 degrees of freedom and both of the joints are linear motions, then we will be having two equations, F1 and F2. Okay, then we have, if it is a 1 degree of freedom with pure rotation, then we'll be having only one equation for torque, there is no equation for this force. Okay, so the equation for torque is T1 is equal to dou by dou t into dou L by dou theta 1 dot minus dou L by dou theta 1, where theta 1 is the angular moment or the amount of rotation that is taking place on that single revolution. So based upon the system degrees of freedom, you will be deriving the required number of equations. So if I am having only 1 degree of freedom and it follows only the linear motion, then we will be only having one equation, and that is defined by this force equation. We not go for this. So to determine that force equation, we need to first of all derive the expression for L, then differentiate that with the system variable xi. So I will be getting this term. Okay, then I can from this xi, that is a position basically, so on derivating that position I will be getting the velocity. So I will be deriving the finding the partial differentiation of the Lagrangian with respect to the velocity parameter x dot, then differentiating that particular differential term with respect to the time. So the basic concept is that if we consider this as a input variable, then you can see that you need to differentiate your Lagrangian with respect to system variable, then we need to differentiate with respect to the time. So that is what is the basics of this basic concept behind the Lagrangian mechanism. So if this is done for the linear mechanism, and if I'm having a 1 degree of freedom with only rotations, then there won't be no equation for force, there will be only one equation for torque. And now you go if you go for a 2 degree of freedom with one linear motion and one rotation, then the dynamic equation of that system is, it will be having one force equation as well as one torque equation. If it is only having two rotations, then there is no equations for force. You will be having two equations for torque, that is T1 and T2. Okay, so in that case, take this general equation and we need to substitute I equal to 1 and 2. Okay, so this will be more clear when we move on to the examples. So as I told, where L is the Lagrangian and it is defined as the summation difference of kinetic energy K, total kinetic energy that is acting on the system K, and the total potential energy that is acting on the system defined as capital P. Okay, and Fi is the summation of all external forces for producing linear motion for the given robotic manipulator or system. Then Ti is the summation of all external torques that is required for the rotational motion of the robotic system. And theta I is a system variable for revolute joint I, and xi is a system variable for linear or prismatic joint I. So the procedure in order to derive the dynamic equation as described is that first of all we need to derive the energy equations for the given system. That is, we need to find the expression for the total kinetic energy that is acting on system. Then we need to find the total expression for the total potential energy that is acting on system. Then find the difference between them, which gives you the Lagrangian. Okay, so that is step 2. Then develop the Lagrangian equation. Then differentiate this Lagrangian with respect to the required terms, so that we will be first of all considering the general equation which is applicable, and we will be trying to find which are the terms required. Then we will be moving ahead. Okay. So let's take the first example of a how to derive the force or the dynamic equations. The question is, derive the force acceleration relationship for the given 1 degree of freedom system shown using Lagrangian mechanism. So here it says that you have a rigid body of mass m which is attached to a spring with spring constant k, and it moves only in one direction, that is x. So there is a force acting. So we need to derive the expression for this force of this given one dimensional freedom, and it is said that the wheels has negligible inertia. So negligible inertia means it is not having any rotational force right now. Okay, or the rotational force on this acting on the wheels can be neglected for the time being. Okay, so since now system is given is a one dimensional one degree of freedom system, we have one equation, and since from the figure it is showing that it is been moving in a linear direction, there is only one equation, which is the equation of force that is acting exerted on the system. Okay, which is given by F is equal to, okay, I am omitting the suffix I for time. If I am giving it as 1 also it is applicable, but there is no need of giving such numberings because we are only having one single joint in system. So F is equal to dou by dou t of dou L by dou x dot minus dou L by dou x. So my aim in further analysis or the further steps is that first of all I need to derive the expression for L, then I will be differentiating the L with respect to x. Okay, so I'll be getting this entire term. Then I'll be taking the basic expression for L again, and I'll be differentiating with respect to x dot, and the result obtained is dou L by dou x dot. Now I'll be differentiating that resultant with respect to time, so that I'll be getting this entire term. Then I will be substituting into this basic expression. So here we have the system, and this is a required expression to be derived. We need to find the terms of this generalized equation. Okay, so from this system we have the kinetic energy that is acting on system is defined as half mv square, which is equal to, okay, kinetic energy, that since there is no rotational, we only have the linear kinetic energy term. So linear kinetic energy, which was seen from the basic equation, k is equal to half mv square, which is equal to half m x dot square, since we know that velocity can be expressed as the derivative, okay, derivative of the position with respect to time. So here we can see that this robotic or this cart or the simple 1 degree system gets displaced by an amount of x from the origin. Okay, so that if I am differentiating that linear displacement x with respect to time, I will be getting the velocity. So on substituting, I will be getting k is equal to half m x dot square. Instead of v, I am substituting x dot. Then the potential energy of the system, since we can see that this rigid body is being linearly displaced by the spring. Okay, so it's with respect to, so this spring is getting displaced along the x direction. So the potential energy, as seen from the basic concept, it is defined as half k x square, where k is a spring constant and x is a linear displacement amount. Okay, so now we have k and p, that is a total expression for kinetic energy and potential energy. So Lagrangian is defined as L is equal to k minus p. On substituting, I will be getting half m x dot square minus, so there is a minus missing. Okay, so that will be updating minus half k x square. Okay, so now I need to differentiate with respect to x, so that I will be getting the first term. So dou L by dou x is equal to dou by dou x of the L term, that is half mx dot square minus half k x square. So I am on expanding the dou by dou x to each of the terms, that is dou by dou x of half mx dot square minus dou by dou x of half kx square. So in this case, you can see the first term doesn't have any terms with respect to x dot is different from x. Okay, because x dot is equal to dou x by dou t. Okay, so this term will be giving you a 0, and here you can see this has an x term, where dou by dou x of x square, or dou by dou x of xn is equal to n into x minus 1. Okay, n into x raised to n minus 1. So here half minus of half k into n is 2, so 2 into x of n minus 1, that is n x of 2 minus 1, which is equal to 1. So half minus half k into 2 into x, so this 2 and this 2 gets cancelled, and I will be getting minus kx, which is marked as equation number 1. So I got the expression for this. Okay, now I'm going to find the expression for dou L by dou x dot. So that means I need to differentiate this general equation with respect to x dot first of all. So dou L by dou x dot is equal to dou by dou x dot of the equation expression for Lagrangian. On expanding the similar fashion, I am getting dou by dou x dot of half mx dot square minus dou by x dot of half kx square, where I can see there is no term in this. Okay, the second term doesn't have any terms with respect to x dot, so this is equal to 0. On differentiating this, I will be getting half m into 2 into x dot into x raised to 1. Okay, so this 2 into gets cancelled, and I will be getting m into x dot, so that is m into dx by dt. So equation number 2. So I got this term. Now I need to differentiate this term with respect to time. Okay, so dou by dou t of dou L by dou x dot is equal to dou by dou t of m x dot. So here you can say this is this x dot is a variable which is dependent upon the time, so we need to differentiate this again. So x dot dou by dou t of x dot is equal to dou square x by dou t square, so that dou square x by dou t square is defined as x double dot. So on differentiating this, I will be getting m into x double dot, which is marked as equation number 3. Now I have got the terms which is to be substituted. So I got dou by dou t of dou L by dou x dot as mx double dot, and dou L by dou x as minus kx. So on substituting these equation number 3 and equation number 1 to the expression, I will be getting the first term mx double dot, second term is minus of dou L by dou x, where dou L by dou x is already minus kx, so minus into minus plus, so that is plus kx. So this is a equation, dynamic equation, which represents the motion of the system. Okay, dynamic equation means a force, the expression for force that is been exerted on this given 1 degree of freedom system. So it seems to be very easy. The only concept is that we need to first of all derive the kinetic equation, kinetic energy expression of the entire system, then the potential energy, find the Lagrangian, differentiate with respect to the required equations. So first of all, once we get the system, list out what are the governing dynamic equations by applying the general Lagrangian equations, then find the expression for kinetic energy, find the expression for potential energy, then from that derive the Lagrangian and find out the required terms which is to be substituted in the generalized equation, and substitute those terms, and you can finally find out the expression for the dynamic components, force or torque, that is acting on the system. Okay. So let's look the next example of a 2 degree of freedom system. Okay. So here the 2 degree of freedom system is been shown to you, and it is also said that the assume the wheels has negligible inertia, so that is a rotational or the torque that is acting on the wheels, which is equivalent to the torque acting on a sphere. Okay, that can be neglected for the time being, as mentioned in the question. If it is not mentioned, we need to take care of that. Okay, so this was the question which was asked for the recent university examination of robotics. Okay, so in this system there are 2 degrees of freedom. One is the linear movement of the force of this particular mass, and other one is a rotational movement of the pendulum, which is connected, or the simple pendulum, or this in a concentrated mass which is been um, suspended from the center of this particular cart. Okay, so the cart has a mass m1 which is been attached to a rigid body using a spring which has a spring constant small k, and this gets deflected or displaced by an amount of x in the x direction, and from the center of the cart we have a concentrated mass m2 suspended, which has been suspended by a length of by using a rod of length L, and it gets deflected by an angle rotational amount of theta. Okay, so there are 2 degrees of freedom. One is the linear motion of the cart as seen, and the other one is the rotational or angular motion of the pendulum. So here we will be having two equations. One is equation for mass for force with respect to the linear motion of the cart. Okay, with respect to not with respect to linear motion, with respect to the system variable x, and the other one is the angular or rotational motion of the pendulum with respect to the angular parameter theta. Okay, so these are the two equations. So now our aim is to find the expression for L, and then differentiate that expression with respect to x, x dot and t. Similarly, the same expression needs to be differentiated with respect to theta, theta dot and t. Okay, so we move on to step by step procedure. So here the given system is there, and the total kinetic energy of the system can be obtained by the summation of the kinetic energy of this cart plus the kinetic energy of this pendulum. Okay, so kinetic energy of the cart as seen from the early example, it is equivalent to half m1 into x1 dot square. Okay, previously it was m, so here the mass is specified as m1, so half m1 x1 dot square. And for pendulum we can say that k pendulum is equal to half m2 into v square, mv square. So for m we are having m2, and v we are having the velocity of the pendulum. Okay, so we need to find the expression for velocity. Since it is an angular movement, we need to find the x and y parameters. So this system can be assumed as, if you take this point, we can see that this is a point corresponding to this C. Okay, or this is my fixed point. Okay, so for this fixed point I can have this origin. Okay, and I can see that from the origin it has been displaced by some amount to the another point which is the center of this cart. So you can say that this is something here. Okay, and from this cart you are having the pendulum distance from here to B. Okay, so this is my end point. So I need to find the velocity with respect to the origin to this point B, which is from this origin to this point of M2. Okay, or that is a end of the pendulum. So we need to find this VB, which is a velocity of the point. So in this general case, VB is defined as VA plus VBA, that is velocity from the origin to the point A, and from velocity from point A to point B. Okay, so in terms of our given system, it can be this is equal to 0, and B is replaced as P, and point A is replaced as C, that is on the cart. So we can say that VP is equal to VC plus V velocity of C bar A bar P. Okay, now if you find the point from 0 to cart. So in this case there is only linear displacement, or the displacement is only in the direction of x. Okay, so I can say that velocity in from origin to this point is equal to that derivative of that particular displacement, that is dx by dt, because we know there is only displacement in the direction of x. Okay, and that is by the amount of x, so dx by dt. And for point from this to here, you can see there is an angular displacement. So this angular displacement has both x component as well as y component. Okay, so for this angular displacement, the x component will be in this direction and y component will be in this direction. Okay, that is in the negative y direction. Normally if we are having x in this direction, we will be taking x in the opposite direction if it is not mentioned. In some cases you may be having positive x direction mentioned directly along this direction, and the positive y direction explicitly defined in the question itself, it is downward. If it is there in the downward direction, you can take it as positive, but in case of such absence of such definitions, you need to take the direction of y in the conventional method, which is in the upward direction, as positive. Okay, so here you can see along the x you have the sine component. Okay, so Lm, so L cos theta is in the minus direction and L sin theta is in the x direction. So I am going to say that velocity component along the x direction is d of x component, that is L sin theta by dt of I cap, minus d by dt of the y component. Okay, I have said minus because I can see that L cos theta, which is a y component, is in the minus y direction. So minus d by dt of L cos theta into j vector. So on differentiating this, I will be getting L into sin theta's derivative is cos theta. So L cos theta into, since theta is a system variable, which is again depending upon time. Okay, we know that the angular velocity. Okay, so that is theta dot. So L cos theta into theta dot into I cap, minus then cos theta's derivative is minus sin theta. So minus of minus L sin theta into theta dot of j cap. Okay, so this minus and minus gets can multiplied and converts to positive. So Vp is equal to x dot I plus L cos theta theta dot I cap plus L sin theta into theta dot into j cap. So combining the I cap terms or I vector terms, so Vp is equal to x dot plus L cos theta theta dot the whole into I cap plus L sin theta theta dot into j cap. Okay, so I got the uh, vector representation of the velocity. Now to find Vp square, that is square of a x I cap plus j y j cap is equal to x square plus y square. So basic concept, Vp square is equal to x dot plus L cos theta into theta dot the whole square plus L sin theta into theta dot the whole square. Now I can substitute this Vp square into the pendulum expression. So on substituting, I will be getting k pendulum is equal to half m2 into the expression for Vp square, that is x dot plus L cos theta into theta dot the whole square plus L sin theta into theta dot the whole square. Now I can open up these brackets and apply the applying the properties and find the individual terms like this. Okay, this is a combined term, so this can be written as a plus b square. Okay, a plus b the whole square is equal to a square plus b square plus 2ab cos theta. Okay, so you are going to not 2b cos theta, a square plus b square plus 2ab. So on expanding that, using that, I am getting the total kinetic energy is equal to k cart, that is half m1 x dot square plus half m2 the expression for Vp square. Now I am going to expand this in this step, that is half m1 into x dot square plus half m2 into a square, that is x1 dot square plus b square. B square means L cos theta theta dot the whole square plus 2 into ab. 2 into a is x dot and b is L cos theta into theta dot. So 2x dot L cos theta into theta dot plus the other term L sin theta dot sin theta into theta dot the whole square. Now on here you can see this term L cos theta theta dot square plus L sin theta into theta dot square. So here if I am taking here you can see that L square if I'm opening this bracket, this is equal to L square cos square theta theta dot square. Similarly, here you will be getting L square sin theta square into theta dot square. So we know the trigonometric identity cos square theta plus sin square theta is equal to 1. So on combining this term and this term, I will be getting L square into theta dot square the whole into cos square theta plus sin square theta. Okay, so I can replace this big equation like this. K total is equal to half m1 x dot square plus half m2 into x dot square plus L2 square into theta 2 square. Okay, the cos square term and sin square terms, when summed, it is equal to 1 plus the remaining term, that is 2 x dot L cos theta into theta dot square. Okay, now here you can see that there are two terms of x dot square. Okay, so we can combine these two terms. So k total is equal to half m1 m2 whole into x dot square plus half m2 into, you need to expand this to the entire brackets, so half m2 into L2 square theta theta dot square plus 2 x dot L cos theta into theta dot. So I have derived the expression for total kinetic energy. Similarly, for this given figure, the potential energy is also expressed in terms of the summation of the potential energy acting on the cart plus potential energy of the pendulum. So we know the general expression for potential energy of the cart is equal to half k into x square, which is based on a spring. Since there is a spring, we are saying that p cart is equal to half k x square. And for pendulum, the general expression from the basic concepts of pendulum in our physics or dynamic courses, it is m2 into g into L of 1 minus cos theta, that is mgh, where h is equal to L into 1 minus cos theta. So the derivations can be obtained from your lower classes picture, or you can even Google also. I'm not going to the derivation. So p pendulum is equal to m2 g L into 1 minus cos theta. It's a simple process. Okay, that means you will be having the total length L and the cos term. So this is the height, total height is this. So here you can see the difference, the mass is acting on this particular amount. Okay, so this is the total length, and here you can see up to this you are having the L cos theta, okay, the term in this. So this is a basic height, so that is 1 minus cos theta. So simple procedure, we can see it. So the total potential energy P is equal to, combining these two terms, half kx square plus m2 gl into 1 minus cos theta. Okay, so now we have got the expression for kinetic energy, total kinetic energy, and the total potential energy that is acting on the system. So the Lagrangian is given by L is equal to k minus p. Substituting the expression for k and substituting expression for p, I got these two expressions. So this is a basic equation which we will be using in order to find the dynamic equations. Okay, so we have this basic equation, and we know that there are two dynamic equation. One is the expression for force and the other one is the expression for torque. So first of all, I will be considering the expression for force. So where I have F is equal to d by dt of dl x dx dot minus dl by dx. So I need to first of all derive or find the derivative of this Lagrangian with respect to x, then find the derivative of the Lagrangian with respect to x dot, then that result should be partially differentiated with respect to time. So first of all, finding dou L by dou x. Dou L by dou x is equal to dou by dou x of the expression for L, that is half m1 m2 whole into x dot square plus half m2 into L2 theta dot square plus 2 x dot L cos theta theta dot minus this term, that is minus half k square plus m2 g L into 1 minus cos theta. Okay, now I can take this dou by dou x into, opening the brackets, I will be getting dou by dou x of half m1 plus m2 the whole into x dot square plus dou by dou x of half m2 into L2 theta dot square plus 2 x dot L cos theta theta dot, then minus dou by x of half kx square plus m2 gl 1 minus cos theta. So here you can say this term doesn't have any x term, so this is equal to derivative of this term with respect to x equal to 0. Here also this term also doesn't contain any x term, it is only having x dot. Okay, so there is no x term, so this is also equal to 0. Now coming to here, you can see the first term has some x terms, but the second term is not having x term, so this is equal to 0. So you need to only find the derivative of this. So derivative dou by dou x of 1 by 2 kx square is equal to 1 by 2 into 1 by 2 into k into 2x raised to 2 minus 1, that is x raised to 1. So 1 minus 1 by 2 k into 2x x. Okay, so these 2 and 2 gets cancelled, and finally you will be getting dou L by dou x equal to minus kx. So this is equation number 1. So I got the expression for this term. Okay, now similarly I am going to find the expression for dou L by dou x dot, so which I get dou by dou x dot of the entire terms. So here you can see that on expanding, opening up the brackets, dou by dou x dot of 1 by 2 m1 plus m2 into x dot square plus dou by dou x dot of, I'm expanding to each of the terms because this has x dot and this is not having an x dot. Okay, so to differentiate that in your expression, dou by dou x dot of half m2 l2 theta dot square plus dou by dou x dot, expand this also, it is half m2 2x dot l cos theta into theta dot minus dou by x dot of the entire term. So this doesn't have any x dot term, so this is equal to 0. This has some terms of x dot, so it should be considered. So this is also not having any x dot, the second term is also not having any x dot term, so this can be equal to, this will be equal to 0, and this has some terms, the first term has some terms of x dot. So this term half m1 m plus m2 is a constant, and the only term which has to be taken differentiated is x dot whole square. So this is equal to dou by dou x dot of x square, that is equal to 2 into x dot. So I will be getting m1 plus m2 into x dot, similar to the previous case. And here you will be getting these 2 and this 2 gets cancelled, and you can see that m2 l cos theta into theta dot is a constant right now. So only the variable is x dot. So if I'm finding dou by dou x dot of x dot is 1, because n is equal to 1 here. So 1 into x into 1 minus n minus 1, n minus 1, that is 1 minus 1 equal to 0. So any term raised to 0 is equal to 1. So I'm getting m2 l cos theta into theta dot. Okay, so on neglecting the 0 terms here, I'll be getting the final expression as dou L by dou x dot equal to m1 plus m2 into x dot plus the 1 plus is additional here, that will be removing m2 l cos theta into theta dot. Okay, now what I have to do, I need to differentiate this expression with respect to time t. Okay, so this is the basic expression for Lagrangian. I have got this term and I also got this term. Now I need to find the derivative. So dou by dt of dou by dou t of dou L dou x dot is equal to dou by dou t of the expression, that is m1 plus m2 into x dot plus m2 L cos theta into theta dot. Okay, so on expanding the brackets, dou by dou t of m1 plus m2 x dot plus dou by dou t of m2 L cos theta into theta dot. So the first term, this is a constant, and you need to only differentiate this term with respect to time. So this is equal to d square x by, this is dx by dt. So on again differentiating with respect to time, you will be getting d square x by dt square, so that is x double dot. And here you can see there are two terms. One is cos theta, which is a term depending upon the time t, and the other one is d theta by dt, again depending. So here you need to apply the product rule. So on applying the product rule, that is u d by dt of uv is equal to derivative of u into v minus derivative of minus derivative of u into v plus u into derivative of v. So derivative of u is cos theta's derivative is minus sin theta. Okay, so I'm getting minus m2 and l on constant, so minus m2l into sin theta, then cos theta is minus sin theta into theta dot. Okay, because we need to the theta alone is the term where that is depending upon the time, it's not the entire cos theta. Okay, so but we need to differentiate. So sin theta minus sin theta into d theta by theta, so that d theta by theta can be defined as theta dot. So on deriving this, that is this is v and this is u. Okay, so minus sin theta into theta dot, so that comes theta dot square. Okay, plus m2 into u, that is cos theta, into derivative of v, that is derivative derivative of theta dot is equal to theta double dot. So that is equation number 3. So now I have the basic expression for force. The first expression for d dou L by dou x as minus kx, dou L by dou x dot as m1 plus m2 into x dot plus m2 L cos theta into theta dot, and the third term, that is dou by dou t of dou L by dou x dot, as the equation number 3. Now I can substitute equation number 3 and equation number 1 to this expression for force, so that I will be getting force is equal to m1 plus m2 x dot minus m2 L sin theta into theta dot square plus m2 L cos theta into theta double dot minus dou L by dou x, that is minus k. So minus into minus plus kx. So this is a first dynamic equation of the given two-dimension degree of freedom system. The similar fashion we need to determine the expression for the second dynamic expression, that is the torque. Okay, that is T is equal to dou by dou t dou L by dou theta dot minus dou L by dou theta. So I have the expression for Lagrangian. Now instead of x, I am going to differentiate this expression with respect to theta. So dou L by dou theta, on expanding again here on and opening the brackets, I will be getting dou L by dou theta is equal to half m1 plus m2 x dot square plus dou by dou theta of m2 on expanding to second term, and this one is dou by dou theta of the third term. So on again expanding this further, I will be getting dou by dou theta of half m1 plus m2 the whole square, the whole into x dot square plus dou by dou theta of half m2 L2 theta dot square plus opening dou by dou theta of 1 by 2 m2 into 2 x dot L cos theta into theta dot minus then dou by dou theta of half k square, then minus dou by dou theta into plus. Okay, so minus dou by dou theta of m2 g L into 1 minus cos theta. Okay, now you can see the first term doesn't have any terms with respect to theta, so it is equal to 0. The second term also doesn't have any term with respect to theta, it is only having theta dot, so that is also equal to 0. The third term has a term with respect to theta, so I need to differentiate. So this 2 and this 2 gets cancelled, so I'll be getting m2 x dot L into dou by dou theta of cos theta is minus sin theta, so that minus comes here, so minus sin theta into theta dot, so I written the theta dot here, and this term is not having any terms of theta, so that's equal to 0. On this side you will be getting mgl into 1, that is equal to 0 because it is not having theta, or else you can see dou by dou theta of 1 minus cos theta. So 1 is differentiated with respect to theta, since a constant it is equal to 0, and here dou by dou theta of minus cos theta, so derivative of cos theta is minus sin theta, so minus into minus plus sin theta, so I will be getting minus m2 gl sin theta. So this minus outside, so this minus gets cancelled with the derivative of this. Okay, so I'm getting dou L by dou theta is equal to minus m2 x dot L into theta dot sin theta minus m2 gl sin theta. Okay, so I got this term. So similar in the fashion, I had to differentiate the Lagrangian with respect to theta dot, which gives me dou by, on expanding, I have expanded, I am not going to explain this. Now I am going to explain this. So on expanding the opening the brackets and expanding, I will be getting dou by dou theta dot of half m1 plus m2 x dot square plus dou by dou theta into half m2 L2 into theta dot square plus dou by dou theta dot into half m2 2 into, okay, I am expanding this to here, so half m2 2 x dot L cos theta into theta dot minus dou by dou theta dot of half k x square minus dou by dou theta of m2 gl 1 minus cos theta. Okay, so this term doesn't have theta dot square, so it's equal to 0. This has some terms, so on differentiating you will be seeing this entire term half m2 L square is constant and only the variable is theta dot square, so dou by dou theta of theta dot square, which is equal to 2 into theta dot raised to 1. Okay, and this term you can see it also has one theta dot square, so 1 by 2, so this 2 and this 2 can cancel, so m2 into x dot L cos theta into dou by dou theta dot into theta dot, that is equal to 1, and here it is doesn't have any theta dot square, so it's equal to 0, and this is also equal to 0. So I get dou L by dou theta dot is equal to m2 L2 theta dot plus m2 x dot L cos theta. Okay, so I got this term. Now I need to differentiate this equation number 6 with respect to time. Okay, so dou by dou t of dou L theta dot is equal to dou by dou t of m L square into theta dot plus m2 x dot L cos theta. So on expanding, dou by dou t m2 L2 m2 L square theta dot plus dou by dou t of m2 x dot L cos theta. So here we will be getting m2 L2 into d theta by dt. Okay, dou by dou t of d theta by dt is equal to dou square theta by dou t square. So that is equal to theta double dot plus, here you can see dx by dt. Okay, so this is a variable with respect to time, as well as cos theta is again a variable with respect to time. So we need to apply the product rule here also. So m2 into derivative of u, that is x double dot into L into v. Okay, u into du by dt into v, that is cos theta. V is cos theta and du by dt is x double dot minus not minus plus m2 into x dot L derivative of v, that is u into v dot v dash, that is derivative of cos theta is minus sin theta into theta dot. So that minus comes here. Okay, so finally I got the expression for dou by dou t of dou L by dou theta dot is equal to m2 L2 theta double dot plus m2 x double dot L cos theta minus m2 x dot L sin theta into theta dot. Okay, now on substituting, so we have the three basic equations and which is necessary for substituting in the expression for torque. Now on substituting these expressions, I will be getting equation number 7 and equation number 5. I will be getting t is equal to m2 L theta double dot plus m2 x double dot L cos theta minus m2 x dot L sin theta into theta dot. That is a term for dou by dou t of dou L by dou theta dot minus of this term. So minus of what is dou L by dou theta, that is minus of m2 x dot L theta dot into sin theta minus m2 gl sin theta. Okay, so if I'm taking this minus inside, I'll be getting this term as positive. Okay, so I got plus m2 x dot L theta dot into sin theta, and this minus into minus again plus, so plus m2 gl sin theta. So here you can see that these two terms are just the reverse. So this is minus x and this is plus x. Okay, it's similar, just the sign. So these two terms get cancelled. So finally I'll be getting the expression for torque t is equal to m2 L square theta double dot plus m2 x double dot L cos theta. So these are cancelled. So plus m2 gl sin theta. So for the given 2 degree of freedom, we have the dynamic equations given by equation number 4 and 8, that is f is equal to m1 plus m2 into x double dot minus m2 L sin theta into theta dot square plus m2 L cos theta into theta double dot plus kx, and torque t is equal to m2 t L2 L square, not L2, L square theta double dot plus m2 x double dot L cos theta plus m2 gl sin theta. So these are the two equations. You can end up at this. Now if you require to if you need to express this in terms of in matrix format, you can also convert this. Okay, so in matrix format, f matrix of f and t ft is equal to, so here you will be having the variable of x first of all, then the variable of theta, torque. Okay, force. So for force, it depends upon the x. So x dot x double dot plus x dot plus the constant terms. So from the first equation, I have the expression the factor of multiplication for x double dot is m1 plus m2, and the second term is x double dot. So I am examining whether I am having an x double dot term in the first expression for force. So I have m2 L cos theta, so I have written that also here. Okay, now coming to the coefficients for the torque, I am checking whether I am having any terms for x double dot. Yes, I have. So that is m2 L cos theta, and for theta double dot I have m2 into L square. So I am writing this m2 into L square here. Okay, then plus the terms for the single derivative of x and theta. Okay, so I have x dot and theta square. So on examining the first expression, I don't have any terms for x dot square, so that is equal to 0, but I have a term for x dot theta dot square, so that is minus m2l sine theta. And comparing the second term, I doesn't have any terms for x dot square or theta dot square, so I am putting zeros. The corresponding questions is zeros. Then I have two remaining constants in first expression and second expression. For first expression it is kx, and second expression I have m2gl sin theta. So this is a matrix format. So it is not needed that we need to always express this matrix format, but if required we can also express the equations, dynamic equations of the expression of a system even matrix format. Since we have seen that for kinematic equations as well as in velocity kinematics we have expressed the entire thing in matrix format, so here also the dynamic equations can be expressed in terms of matrix format. Okay, so that's the end of this lecture. So in the next lecture we will be discussing some more workout problems. Okay, thank you.